Welcome to this Eonfusion tutorial on data structure. We will look at how data is structured in Eonfusion and how this affects the way we can analyse, interrogate, manipulate and visualise data. It is assumed that you've already seen the overview tutorial. There are a number of different ways in Eonfusion to access a visual representation of the data structure. The easiest is to right-click on an object in the data flow, click Output Data Structure, and this will bring up the data structure browser. In this case, we're looking at the structure of a single raster dataset, the aerial photo seen draped on the bathymetry in the scene above. In the data structure browser, the dataset is contained in this table, with the name and type of the dataset in the top heading. We also have an attribute group named 2D raster, which contains a number of attributes, red, green and blue. If we click the Details tab, we can get more details about the dataset as a whole, for the attribute group, or for individual attributes by hovering over the relevant area. By right-clicking on an attribute group, you get the option to view the data in that group in a table, and by right-clicking on individual attributes, you get the option to graph that attribute. You can also create a persistent version of the data structure browser in the New View menu by right-clicking on the data flow background. You will also notice that the Scene Contents pane has a similar format to the data structure browser, and you can open a data structure browser by right-clicking on a visualizer. The data structure browser is used for a number of different purposes in Eonfusion, which you will see in this and other tutorials. The data structure browser will contain all the datasets present at the point in the data flow it is accessed. If we look at the data structure of the Getting Started Scene 1 object, you will see all the datasets that are piped into that scene stacked vertically. And if we look at the scene object of the slightly more complex Getting Started Scene 2, once again, for each branch in the data flow, the data structure browser contains all the relevant datasets. In this case, you will notice that the datasets are not only arranged top to bottom, but also left to right, with the most recently modified or created dataset on the right for each branch in the data flow. For example, the fusion operator has two input pipes, and the operator creates a new fused dataset, which are all visible in the data structure view. The input datasets to the left, and the newly created fused dataset to the right. You also notice that some datasets are linked, indicated by this line. A bolder line connecting the actual linked attributes or attribute groups will be displayed when you hover over those attributes. You also notice that there are two main data formats in Eonfusion: vector data and raster data. We will now take a more detailed look at the structure of each of these separately. First, we will look at how raster data is stored in Eonfusion. Raster data is an efficient way of storing regularly gridded data and consists of cells stored in a regular array or matrix. Images, such as the aerial photos shown in the above scene, are familiar examples of raster data. This raster is a colour image, so has the standard red, green and blue attributes. If we zoom in on the scene, we can see the individual cells in the raster, with the colour for each cell being generated from the combination of the value of the red, green and blue attributes for that cell. Each cell may have any number of attributes, but because of the regular arrangement of cells, the geometric or geographic location of each cell does not have to be stored individually. Instead, the cell locations can be easily calculated from the stored location of a single cell and the grid spacing for each dimension. The extents of the locations are accessible in the Details tab for the raster attribute group. As well as colour data, rasters could store data values such as elevation or temperature, or the attributes may represent a series of layers or time series of data measurement. For more details on how to customize the way you can visualize raster data, please see the Visualizers tutorial. We will now look at how vector data is structured in Eonfusion. If we look at the Getting Started C2, we'll see that along with the aerial photo, we've also draped habitat information onto the bathymetry. If we look in the data flow, we can find the habitat shapefile data source, and we can create a new scene and pipe the data source into this to view this dataset by itself. If we look at the data structure of this dataset, we'll see that vector data is structured differently to raster data. We still have the dataset in a single table, with the top heading showing the data format and dataset name, and we also have a number of attribute groups. In the left-hand column are the spatial feature attribute groups, 1D lines and 2D surfaces in this case, with the relevant spatial feature attributes, if any. You will notice that the 1D lines attribute group does not contain any attributes. On the right hand side we have the vertices attribute group, which contains the vertex attributes. These attribute groups uncover the structure of vector data, which consists of spatial features. In Eonfusion, these can be points, lines or surfaces, whose geographic or geometric position are defined by vertices. If we open up the scene we just created, by right-clicking on the 2D surface spatial feature group, we can create a visualizer that will give a visual representation of our 2D surface spatial features. For each spatial feature, it is the mapping of the vertex attributes onto the X, Y and Z axis of the scene that determines the geographic or geometric position of that spatial feature. This is an important concept in Eonfusion. When visualizing vector data in a scene, it is the spatial features being visualized, with the vertex attributes determining the location of the spatial features. In this case, looking at the properties of the visualizer, we see that logically the vertex attributes X and Y have been mapped to the X and Y axis in the scene. For more details on how this is done, see the visualizers tutorial. At the moment, it looks like a single 2D surface has been drawn. But if we click on the surface, we can see that smaller areas of the surface can be individually selected. Each individually selectable area is an individual spatial feature. If we look at the data structure of the dataset and view the table of the 2D surface spatial features, you will see each item or row in the table corresponds to an individual spatial feature that is individually selectable in the scene. In the scene, by holding Alt and hovering over an individual spatial feature, you will see a small box appear with details about the spatial feature. The top line is the XYZ position of the cursor in the scene. The second line is the spatial feature index, which corresponds to the item's index number in the table view, and below this are the values of the spatial feature attributes for this spatial feature. In this dataset, we can also create a visualizer on the 1D lines spatial feature group, which in this case corresponds to the perimeter of each of the 2D surface spatial features we saw before. If we look at the data structure of this dataset again, we can see in the Details tab that both the spatial feature groups contain 62 items, but the vertices group contains 6,217 items. This is because internally, Eonfusion stores links between each spatial feature and the one or more vertices that store the location of that spatial feature. If we zoom in on a selected line spatial feature in the scene, we can see that its shape is made up of a number of individual line segments. Each of these segments is known as a primitive, the location of which is determined by a vertex at each end of the line segment. Note in the case of 2D surface spatial features, the primitives are triangles, so the shape of an individual surface spatial feature is determined by a mesh of connected triangle primitives, and the location of each triangle primitive is determined by 3 vertices, one at each point of the triangle. If we look at the data structure of the bathymetry dataset, we have a 0D point spatial feature attribute group. And from the Details tab, we can see that each point in the dataset is an individual spatial feature, whose position is determined by an individual vertex with attributes X, Y and Z. And we can see in our scene that each of these point spatial features is individually selectable. To the right of the dataset in the data flow is a triangulate vertices operator. Looking at the data structure, we see the operator has created a single 2D surface spatial feature. If we look at the properties of the operator, we can see that we are triangulating based on the vertex attributes X and Y. This means we are creating a single 2D surface spatial feature consisting of a mesh of triangled primitives that connect all the vertices in the dataset into trios of neighbouring vertices based on the vertex attributes X and Y. Once again in the scene, we can see this single 2D surface spatial feature is individually selectable. Above the bathymetry data source is the GPS sensor data source. This has been manipulated in a similar way using a linearized vertices operator to create a 1D line spatial feature. In the scene, we can see that for the bathymetry dataset, we can visualize the 0D points and the 2D surface. But in both cases, the location in 3D space in the scene is determined by mapping the X, Y and Z vertex attributes onto the X, Y and Z axes in the scene. For the GPS track, we can visualize the 0D points spatial features and the 1D line spatial features. And in both cases, we have mapped the vertex attributes lon and lat onto the X and Y axis in the scene, but we have also mapped the vertex attribute date time onto the slider. The mapping to the slider allows us to control the time range of the data being visualized. So in our scene, we can visualize vector data as point, line or surface spatial features in 4 dimensions by mapping the appropriate vertex attributes onto the X, Y and Z axis and the slider to define the location of the spatial features in our 4D space. This tutorial has provided an introduction to the way data is structured in Eonfusion. Please take the time to view our other video tutorials to learn more about the components you have seen here.